Alright, in this lesson we're going to start talking about work and energy. And the very first thing we start talking about work is, if we're talking about work, we need to introduce a new type of way to work with vectors. And this is what's called the scalar product. And so what work is defined as is the product of force and displacement. F times S. I'm using S here for displacement. And there are two ways that you multiply vectors or get a product of vectors. One of the ones which we're concerned about today is what's called the scalar product or dot product. That has a result which is a scalar. So you take two vectors, multiply them together, and you get a scalar result, something that's just a number. One thing to point out about the scalar product is the one piece of information that you really lose is information about direction. That the scalar product has no information about direction. Which, if we think about what work is a scalar to begin with, just like energy is a scalar, so there's no direction associated with it. The other way to multiply vectors, and we'll get to this in a little bit later, is the vector product or the cross product. And the result of the vector product is another vector. So you multiply two vectors together and you get a third vector as your result of that multiplication of two vectors. So we'll take a look at that in a little bit more detail later on. Probably some good examples of the scalar product, something like torque is a great example of the scalar product, or angular momentum is another good example of the scalar product. So we'll look at those in a little bit more, the vector product. Torque and angular momentum are good examples of the vector product. So we'll look at those in a little bit more detail when we get to those topics. We also may look at what happens if you have two vectors that you're taking a vector product of, and then the scalar product of a third vector, and what happens if you're doing something like that. So if we look at the dot product or the scalar product, one way that we can calculate the value of that is by knowing the magnitude of the two vectors and then the angle between them. It's worth pointing out with the cross product, you can also calculate the magnitude of the cross product or the magnitude of the vector product by knowing the magnitudes of the two vectors and the angle between them. In this case, magnitude of force times magnitude of displacement times cosine of theta equals the work done. But there's another way we can calculate the scalar product by using vectors in unit vector notation. And this might be a more useful way when we look at vectors in general when we're dealing with vector calculations. And the way to do that is to take the x components of a and b, multiply them together, take the y components of a and b, multiply them together, take the z components of a and b, multiply together, and then add those all up. So you could see what happened if we had if for some reason we had like a 6-dimensional vector. Well, we just have 6 terms here that we're going to add up. There's some other mathematical properties of the scalar product or dot product that are useful to remember and useful to know. One of them is if a and b are parallel to one another, then the dot product of a and b is just equal to the magnitude of a times the magnitude of b. Well, in that case, your angle between them would be 0. The cosine of 0 is 1. And so we just get the magnitudes multiplied together. Now, if they're what's called anti-parallel means they point in exactly the opposite direction. The angle between them is 180 degrees. We introduce a negative sign in there. Basically, the cosine of 180 is -1, and so that introduces the negative sign. The third one that's important to remember is if a and b happen to be perpendicular to one another. Well, if perpendicular, the angle between the two vectors is 90 degrees, the dot product is 0 regardless of how big those vectors are. So let's do a quick example problem calculating out the dot product dealing with work. So we're going to have a constant net force is applied to an object, and I've made that net force 5I hat minus 4J hat newtons, and it's going to act on an object as it undergoes a displacement of 3I hat plus 2J hat meters. And I want to calculate the work done on this object. Well, work is equal to force dot displacement. Or another way to do this would be to say, in general, the x component of force times the x component of displacement plus the y component of force times the y component of displacement plus the z component of force times the z component of displacement. So that's another way we could calculate this out. If we plug in our numbers, we'd have 5 times 3, the x components multiplied together, plus -4 times 2, the y components multiplied together, plus, 0 times 0, there are no z components, no k hat components. And so we get that the displacement is 15 joules minus 8 joules essentially, or the work done here is 7 joules. Now, you might wonder, where does this actually come from? And there are some ways that you can actually reason through this. If you're interested in where that equation comes from in general, come and talk to me and we can kind of work some things out and I can show you why it is this way. There is a reason why it is this way, and it actually comes out of this equation here if you think about it for a few seconds. Now the second example problem that I have is I have a 1,500 kilogram crate that's going to get pushed up a frictionless ramp at a 30-degree angle, 5 meters at a constant speed. And we want to calculate the work being done by this force. The reason why I've done a constant speed is it makes our life a little bit easier. It means that we're in an equilibrium situation. Sum of all forces equals 0. So if we look at the forces, we have weight pulling down, we have the pushing force, which we're going to call F, pushing up, and we have the normal force perpendicular to the ramp. And I want to figure out the work done by all three of these forces. So let's first of all find the work done by the gravitational force. So work done by gravitational force is whatever the gravitational force is times the displacement times the cosine of the angle between them. So we need to find theta. If that angle is 30 degrees here, and this whole angle here is 90 degrees, I'm pushing up the ramp, then the angle between S and F has to be 120 degrees. So you end up with the weight, 1,500 times 9.8 meters per second squared, times the distance, 5 meters, times the cosine of the angle between displacement and force, which would be 120 degrees, this whole angle in here. So we get the work done by gravity is negative 36,750 joules. You might say, well, does it make sense that it's negative? Well, yes. It does make sense that it's negative because if you're pushing something up, the direction of its motion is opposite the direction gravity is trying to pull it. So next step, we'll go with the pushing force. The pushing force is pretty easy. The pushing force times the displacement. We know the displacement 5 meters. So I'm going to find the pushing force. And this is where I use the Newton's first law to figure that out. That the pushing force has to be equal to the x component of the gravitational force. Well, the way to do that would be gravitational force times sine of 30. So I can calculate how big F is, 7,350 newtons. And then I can calculate out what the work done, 7,350 times 5, and I get 36,750 joules is the work done by the pushing force. Cool. Now the last one is the normal force. And the normal force is acting perpendicular to its displacement. So I can actually go to that third of my three kind of general mathematical properties of dot product and say the work done by the normal force is 0. Now we'll come back in this situation when we talk about work energy theorem and try to see, does this result make sense that the pushing force, looks like the pushing force and the gravitational force did the same magnitude of work, just one is negative and then one is positive. So we'll see if that makes sense in the context of this system when we look at kind of our next lesson.